I'm just going to talk about the main reasons for LEDs tending to fail way before their lifespan. Well, their rated lifespan anyway. Now, if you know, whenever you buy like an LED backlit TV or an LED light bulb for a light fixture, you'll see on the box a lot of the time that the actual LEDs are rated for 50,000 hours lifetime and maximum brightness or whatever, and all this BS that they put on the box to get you to buy the product. But the reality of that, especially in LED backlit TVs, in light fixtures it is a bit better than TVs, but I have actually seen some LEDs failed in light fixtures, but mainly I've seen LED TVs fail. And the main cause for LEDs tending to fail is heat. And a lot of the time the LEDs are being overdriven because they're either in a series circuit or the manufacturer adds less LEDs to a device and then overdrives the others that are in there to save themselves money. So they're adding less LEDs, but they're still maintaining the same light output by overdriving the others, and they can get away with that a lot of the time. But those are two of the main reasons why they fail, is because they're being overdriven, which causes them to get really hot, which causes a breakdown in the LED. Now, LEDs will either fail open circuit, which is where the dye bond, which is just basically the bond of the LED, and which holds the whisker inside, and the whisker is a bit like the electrode basically. It's where the dye bond breaks down and normally has a tendency to crack, from what I've seen. And when that cracks, the whisker in the LED can no longer make contact, and it won't emit light because, again, the whisker can't make any contact, so the electrical connection is broken. Or, in rare cases, and I'd say open circuit LEDs, about 90% of the time that happens, but you do get short circuits in LEDs, which I'd say probably about 10% of the time. I've only ever seen, I think, about 3 short circuit LEDs out of about 30 TVs that I've done. But even after a while, a short-circuited LED will get very hot and burn up and then fail open circuit. But with the short-circuit LED, the whisker shorts out, normally because, again, the dye bond cracks. But it'll short out to the other side, and then you'll just have a short across that LED. Now, LED TVs, the main reason why you get no backlight when one LED fails, and it only takes one LED to fail, the reason why you get no backlight is because all the LEDs are in series, and that basically means, if you know anything about circuits, each device depends on each other. So I've got about 9 LEDs here or so. Each LED depends on each other to be able to work properly, and if one fails, the circuit won't be complete anymore and none of them will light. And a lot of the time that's what happens in LED TVs. An LED fails open circuit and the strips can no longer light. Now, in cheaper ones like Vestel TVs, the protection circuit loads the LEDs and it'll detect that one is open circuit, and it'll try to light the rest of them, but it can't because one's not working in the chain, and the protection circuit will cut off and you'll see a flash from the LED strings. It mainly happens on LG TVs, but on Vestel sets they don't do that. So if one LED fails, none of the strip will light up or even give a flash on the screen. So that's what happens. Now, that's in series circuits, but if they were to parallel the LEDs, and by the way, in series they have to apply a very high voltage, which each LED drops about 3 volts, so I've got 9 LEDs here, so times that by 3 roughly, and then normally you add however many watts each LED dissipates on top, but say it's about 27 volts I would need to power all these if they were in series. But A more reliable method was if they was to put the LEDs in parallel and make sure that each LED only receives a low amount of current, but in series that the current provided is enough current for all the LEDs, which is why they get pretty hot. But in parallel, if they was to provide 3 volts across each LED at a low enough current, it'll work fine. And even if one LED does fail over time, it's not going to affect the rest of the strip. But that costs the manufacturer more money to do that in TVs, because they have to then individually wire up each LED and then create the circuitry for a 3.3 volt or 3 volt rail to power all the LEDs. And it's pretty expensive to do that, but it's cheaper to do it in series. Now, another way they could help prevent failures is if they heat sunk the bloody LEDs better. The only heat sink and way for the LEDs to dissipate heat is the copper traces on the LED strips, which it doesn't really take. It takes probably about 1 LED to heat up and dissipate the max amount that the copper trace can take before it doesn't really dissipate much heat after that. And when you've got about 11 LEDs on a very small copper strip, you know, it heats up pretty fast and it won't be able to dissipate the heat much better. If they was to simply add and make the copper trace on the other side of the PCB rather than just the rest of the PCB substrate, which this is not heat conductive, by the way, the only thing conductive on here is the copper. If they was to make the copper all the way through and then heat sink it to the chassis, we probably wouldn't be seeing nearly as much LED failures as we're seeing, but they don't do that. So LEDs just basically get too hot and burn up in no time flat. I think the shortest one I've ever seen is 6 months. I've seen an LED TV fail with a popped LED in the panel, which is just, you know, it's crap. So I'm gonna, now I don't care about these LEDs on here, I've only just done this for a test purpose basically. I'm going to show you how they fail, and I hope this crappy camera can pick it up. I'm just going to screw my tripod on here, but as I said earlier, the dye bond on the LED tends to crack, which when that happens the whiskers can no longer make contact. Now this second LED here, I've used hot air to get these onto this PCB, so that's a lot of heat gone through the LEDs. I'm just going to zoom in, I think it's that one. No, it's not actually, it's this one. Yeah, this fourth one up. Now I'm going to try and get as close as I can, because this camera tends to blur up as soon as you zoom in. Now if you see on the LED, you can see there's a little crack there on the outer casing. Now that's where the negative electrode tab is, and then on this side is where the positive electrode tab is, because the positive electrode tab has a bigger surface area, and this is the negative one, right where that crack is. So it's possible that it's cracking in between the two electrodes because it's not able to transfer heat through the electrodes onto the PCB. And it's cracked right in the middle there, and it only takes a bit of a crack to go through the centre piece here before the whisker gets broken. I'm going to show you this next LED down. Oh, camera's had a meltdown. And if you see here, inside the actual die, and the die is the section in the middle if I didn't say, you can see that it's starting to break down across here. You can actually see it on the inside. That's where it's gotten hot. And this LED was like that before I even took it off the original strip. So that LED there is getting close to breaking down and cracking. And again, this one at the end here. I don't know why the camera's going to pick this up. Oops. And I hate this Sony camera. Hopefully if I get a better lighting condition you can see that. Oh, are you going to pick that up or not? I'm really sorry about this camera work, but I need to get a better camera. Right, there you can see it there. See there's a crack there and a crack there. That's where the one electrode is, and then there is where I think that connects to the negative, right in the centre where that other crack is. And the positive is this end. It's cracking, the die is cracking right where the electrodes, you know, make contact, which is when the light gets produced. And this one at the front again, you can see evidence of it getting hot. And it's sort of split. And that's basically how they fail. Cracks develop in between the electrodes, and then it either shorts out because of this crack, or because of the crack, sorry, or it fails open circuit, so they can't make contact anymore. And that's basically how LEDs fail. And the main cause, in my opinion, is heat. You know, in LED TVs, now this is an edge-lit LED TV, it's an ultra slimline one. Now these edge-lit ones are more reliable because the actual strip has a solid aluminium heatsink to cool all the LEDs. And then that heatsink then connects to the metal chassis of the TV, which also cools it down as well. And that works a lot better because they can actually transfer heat away from themselves, so the die bond doesn't break down as fast. Now this is a 32-inch full array type LED TV, and this has those really small LED strips on them where there's not much heat sinking for the actual LEDs, and they get real hot and then fail. Now I'm going to show you my light that I have here in my room. So this is my LED light. In fact, I'll just turn it on here. So plug that in. There we go. So these are basically just some 12 volt LEDs, and I have a little power supply here. So I've had this for a year now, and I'm running them at 13 volts, which is much more than they're rated, well, about a volt more than they're rated for, and as you can see, I've got them mounted on a aluminium strip, and I've got some little heat sinks situated up and down here, and this gets real hot after being on for a few hours. But I've not had a single bulb fail, and I've seen someone who had a similar setup and they had a bulb fail. And these are wired in series, so there's 3 LEDs that dissipate about 3.5 volts each, because there's a resistor as well across there. But I'm going to show you what happens when you push too much current through an LED with this power supply here. So I'm going to show you what happens when you push too much wattage through an LED. So first off, I'm going to be powering these with 3.3 volts. Oops. And I'm going to show you these burning out as well, because I don't care about them, because they're getting near the end of their lives anyway. That's 3.3 volts. That is really, really bright. That's dissipating, I'd say, probably about 30 watts right now. And just putting my hand across there, I can't get this on the camera, but I can feel that they've actually gotten warm. So put it on to 5 volts. That is very bright. And pretty warm. And I'm going to connect them to a much higher voltage, 12 volts. And you can see they burn up. And they get dimmer as they burn. And you can see it's actually just burnt through this PCB. That might have been from where I hot aired them, but yeah. So we're going to see if any of these still light or not at 3.3 volts. They probably will, but very dim. And one of them's actually short-circuited because my wires are really hot. Yeah, they barely even light, so let's just push this to 12 volts and kill these off because I hate LEDs. Why aren't you dying? Oh well. Yeah, but if you have an LED device or an LED TV, just turn the brightness down and don't run it for more than, I'd say, 6 hours at a time. And that's how LEDs fail, basically. And some of these have failed short circuit and some have blown themselves up open circuit. I hope this just gives you a bit of information. Thanks for watching.